Okay, I raise my hands right now. I know it has been a long video, a long set of lecture, and quite a lot to take in a first go. So I do understand the ordeal you are going through now after studying nuclear physics. That is the 9th video of this particular chapter. But still, in this particular video, or let's say this video as a whole is important because it will give you an outlook about how are the different questions, what are the different concepts, what are the different ideas which are teased by different competitive exams in the past years. So right now for you we have 5 questions from the past competitive, or let's say the competitive exams for the past few years. So here are those questions. Now let's start off with the last part of the discussion in this chapter of modern physics. That is, we are dealing with a few of the questions which came in the most important competitive exam in Indian subcontinent, that is joint entrance examination. So let's discuss few of the problems which came in past years corresponding to this topic. So let's start off with the first problem. It states the radiation corresponding to 3 to 2 transition of hydrogen atom falls on a metal surface to produce photoelectrons. These electrons are made to enter a magnetic field of 3 into 10 to the power minus 4 Tesla. If the radius of the largest circular path followed by these electrons is 10 mm, the work function of the metal is close to. Now, in order to solve this problem, first understand what's happening. An electron is making a transition from the n equals to 3 to n equals to 2. Corresponding to this falling of electron from a higher state to a lower state results in the emission of photon. Now these photons as a whole, they are made to fall on a metal surface. Now these photons, they have energy, so they are now made to fall on metal surface, and while falling on metal surface, they are knocking off electrons. Now it's being said that these knocked off electrons are made to enter a magnetic field region where they perform the circular motion. The radius corresponding to that circular path is also given. So we need to find out the work function. So what we need to do is we need to trace back, or we need to trickle down. What do I mean by trace back or trickle down is there are 3 events which are connected. First, emission of photon through electronic transition. These emission of electrons these emission of photons results into knocking off electrons on another surface. Second event. Third event is the knocked off electrons from the metal surface are moving in a circular path in a magnetic field region. 3 different events. Either I go up from magnetic field or moving in a magnetic field to knocked off from a metal surface to emission of photons. Either I go up or either I come down. So let's start solving this problem. I know that the energy which is let out is equal to energy emitted by the photon. So I'm actually trickling down from top to bottom. So the energy of the photons, I know it's equal to E naught. Let's say E naught is a ground state, 13.6 electron volt, 1 by 4 minus 1 by 9. This comes out to be 5 E naught 36 by 36. Now remember, E naught over here is our 13.6 electron volt. Now the energy, or let's say the photon of this much energy are made to fall on metal surface. So 5 E naught divided by 36 is equal to the work function which we are striving for plus the kinetic energy of the electrons. Implies the kinetic energy of the electrons are 5 E naught divided by 36 minus phi naught. From this, I need to get hold of the velocity or mv or anything. I need to get some information after this expression. Now I will make the connect, but before that, let's analyze what's happening in the magnetic field region. I know mv square by r, the centripetal force, is equal to EVB. Implies mv divided by R E equals to B. I know what is the magnetic field, I know what is the radius of the curvature, I know what is the charge, I know also the mass of electron. The only entity which I don't know is the velocity. I need to get hold of the velocity from this entity. So let's check it out. I have half mv square. Let's denote this as a whole as some constant k. Okay, because if you look at it, the value is constant, so it's k. So I know mv is equal to 2k divided by m. What I'm trying to do is I'm multiplying m in the numerator and multiplying m in the denominator. So I end up getting mv to be 2k by m. So please keep in mind, m will go in the numerator. So mv came out to be 2km, root over 2km. Now I'll use this value in this particular expression. So I have 2km divided by Re equals to B. Now I need to find out the work function, and k, if you look at it, what is our k? K is basically 5 E naught by 36 minus phi naught. So I'll substitute the value of the k over here to exactly evaluate the work function. So I have b square r square e square divided by 2m equals to 5 E naught by 36 minus phi naught. If you put down all the values, if you look at it, we know the value of E naught, we know the value of the magnetic field, we know the value of the radius of curvature, we also know the value of the electronic charge held by the electron, also its mass. If you evaluate this, put down all the values, you will end up getting 1.1 electron volt as the correct answer. So just work it out. The only catch was relating 3 events over here. I have done the that is the relating part, that is from top to bottom. If you want to solve this problem in some other way around, go from bottom to top, right? Go up. I came down, you can go up. So B, 1.1 electron volt is the correct answer. Now moving down. Second question, a metal surface is illuminated by the light of two different wavelengths, 248 nanometer and 310 nanometer. The maximum speeds of the photoelectrons corresponding to these wavelengths are mu1 and mu2. Respectively, if the ratio mu1 by mu2 equals to 2:1 and Hc is equal to 240 electron volts nanometer, the work function of the metal is. Now I know that is, I should use somehow this constant and also relate it to the velocities mu1 and mu2. So I'm just writing it down. So the energy which actually fell on the surface is 1240 electron volt nanometer divided by lambda 1 minus phi naught is equal to half m mass of the electrons into mu1 square. Similarly, 1240 divided by lambda 2 minus phi is equal to half m mu2 square. I know the ratio of mu1 is mu2, so I just divide these two equations and I will end up getting 1240 lambda 1 minus phi. Now please note over here that the lambda 1 which is given is 248 nanometer and the lambda 2 is 310 nanometers. So as I know, lower the wavelength, higher is the energy. So mu1 therefore has an higher energy. This is equal to 4 times, as it's mu1 is to mu2 is given as 2:1. So mu1 square is to mu2 square will come out to be 4. So this is equal to 1240 divided by lambda 2 minus phi. Now you just need to evaluate these expressions because you know what is lambda 1, you know what is lambda 2. Nonetheless, we'll simplify this equation further. So it will come out to be 4 times 1240 divided by lambda 2 minus 1240 divided by lambda 1 equals to 35. So you will straight away get the work function if you put down the values of lambda and simply evaluate this. Working this out, you will end up getting 3.2 electron volt as the correct answer. Sorry, not 3.2 electron volts. This is a wrong answer, this is wrong answer, and this is always the wrong answer. 3.7 electron volt as a correct answer. So work this out. It's simple. You just need to make sure that the values which you put are straight away, because lambda 2 clearly demands and lambda 1 clearly demands you being putting the values in terms of nanometer. Luckily, the values of the wavelength are given in nanometer. The reason being HC. HC is given to be 1240 electron volt nanometer. So as I know, energy is HC by lambda, and HC is, if it's given in like this, I need to put lambda correspondingly. So I will get the phi in terms of electron volt. Moving on, if lambda cu, that is the wavelength associated with copper, is K alpha X-ray line of copper, atomic number is 29, and lambda m naught is the wavelength of K alpha X-ray line of molybdenum, atomic number 42, then the ratio of lambda cu, lambda copper divided by lambda molybdenum is close to. Now, I know that the energy which one gets from the characteristic alpha is this. That is the wavelength which I end up getting is this, copper. Or let's say in case of molybdenum, so this is the wavelength which I am expecting. The energy difference between the two levels in which the electrons are making the transition, inner levels, right, that is denoted by lambda, del ECU or del EMO, if it's related to copper or if it's related to the molybdenum. And I also know that the energy levels of an atom is directly proportional. So, or let's say energy is directly proportional to Z square. That is clearly evident. So if I want to take the ratios of it, lambda Cu by lambda Mo, it will be, if you look at it, in the ratio of del Mo molybdenum to del copper, which will come out to be Z molybdenum, Z copper whole square. So I just need to take the ratio of 42 is to 29 and take its square. To work out, it will close to 1.9 and it comes around 2.0304. So the closest thing which I know is 1.99. So I'm being asked to find out what is the close to. So A 1.99 is the correct answer. Going on. In an hydrogen-like atom, an electron makes transition from a state with a quantum number n to a state with a quantum number n minus 1. If n is much larger than 1, then the frequency of the radiation emitted is proportional to. Now, the energy associated with a particular level, or let's say it's making a transition, so it's Hc by lambda equals to E naught, again 13.16, 1 by n minus 1 square minus 1 by n square. This is the relation related to the difference in the energy levels and the wavelength of the light which I expect. So simply work this out, that is 1 by lambda is equal to E naught by Hc. In the denominator I will have n square, n minus 1 whole square. In the numerator, I will have n square minus n minus 1 whole square, which in turn will come out to be, again writing E naught by Hc. In the numerator, I will have 2n minus 1 divided by, in the denominator, it's again n square n minus 1 whole square. If I want to work this out, I see that the lambda is proportional to, let's say, the lambda is proportional to n square n minus 1 whole square divided by 2n minus 1. Now this is the relation between the lambda and n. Again, taking n common from the denominator, I will end up getting lambda is proportional to n into n minus 1 whole square divided by 2 minus 1 by n. Look closely, given the fact n is much greater than 1, I can clearly figure out that the lambda, the highest power being n cubed, so lambda is proportional to n cube. If lambda is proportional to n cube, it implies the frequency is proportional to 1 by n cube, because I know they are inversely related. Hence C, 1 by n cube is the correct answer. Now, moving on. Hydrogen 1H1, deuterium 1H2, single ionized helium 2He4 plus, and double ionized lithium 3Li6 plus 2 all have one electron around the nucleus. Consider an electron transition from n equals to 2 to n equals to 1. If the wavelengths of emitted radiations are lambda 1, lambda 2 and lambda 3 and lambda 4 respectively, then approximately which one of the following is correct? Now I know that the energy associated with their transition is Hc by lambda I put it, whether I can be 1, 2, 3, 4, is equal to E naught 1 by 1, 4 into Z square. So it's 1 by lambda I is equal to E naught by Hc into 3 by 4 Z square. Again, simplifying it further, lambda I comes out to be 4 Hc divided by 3 E naught Z square. So it clearly states that the higher, or let's say I write over here it's Zi over here. So higher your atomic number, lower will be your wavelength. So over here in hydrogen I have 1, in deuterium as well I have 1, in single ionized helium I have 2. So if this corresponds to lambda 1, this corresponds to lambda 2, lambda 1 is equal to lambda 2, that's done deal. So if just by going by my objective skills, I find out that the only condition in which lambda 1 is equal to lambda 2 is the fourth one. So it means fourth is the correct answer. Now we have solved this problem, but let's look at it as a conceptual question. That is, I want to truly solve it, not get the marks out of it. So lambda 1 is equal to lambda 2, that's done deal. And if you look at for the helium, you find the factor over here will come out to be 4. So it will be, 1/4 of lambda 1 and lambda 2. So if lambda 1 equals to lambda 1 equals to lambda 2 equals to lambda naught, then lambda 3 is equal to lambda naught by 4. And subsequently, lambda 4 will be lambda naught by 9. Reason being, lithium has an atomic number of 3. So 3 square is 9, so 9 goes in the denominator. Hence, this is the correct answer. Just equating all those.
While going through the lecture, if you face any doubt, you can post your doubt for free at askIITians.com. In order to do so, you first need to navigate to the askIITians.com. Then, while going to that link, you can use discussion board link, which is over here. Clicking on this particular discussion board link, it will take you to a page where under the head of Ask the Experts, you can post your doubt under various categories. And the team of Ask IITians Expert will get back to you between 24 to 48 hours.
Okay, now that we are completely done with the whole chapter of modern physics, done. It's a complete wrap up, close, cut, done. Now, just taking a small trip down the memory lane, what are the different things which we have covered? First off, we discussed what exactly is modern physics. If I'm talking modern for me is what's going on right now. But the physics going on right now is not compatible with the mathematical tools which I have. I don't have those kind of mathematical tools to play around the theories going around right now. So for me, for my intellectual level, for the mathematical tools available to you at class 12, sorry, you are only accustomed to get all the physics between 1900 to 1950. So that's why the modern physics for you is in those 50 initial years of 20th century. I just defined you the timeline. Again, taking the trip down the memory lane. We will also, so if this, it depends upon the scientific development for the initial 50 years. So the initial let's say those developments were to find out the nature of the light. And why did I actually wanted to find out the nature of the light? Because I wanted to know the structure of atom. Okay. Why do you want to find out the structure of atom, and how will the light help you in finding out the structure of the atom? As I said earlier in an example as well, that is, if I want to know anything about a person, he's sitting in front of me, I want to know more, or let's say I want to gather as many as data possible for that particular person. Why? Because I want to know everything about that person. So I will keep on disturbing the person in one way or the other so as to get out a response, and then design a mental framework about his traits, his characteristics, right? Now, so it's stimuli, response, right? So it's like action, reaction. So the action will end up giving me the whole picture. Now, I want to study about atom. Why do I want to study about atom? I don't know. Is it of any use? Yeah, it is. Because if I know what an atom looks like, how it is, I can be able to design new things which will be useful for me. Through chemical reactions, through nuclear reactions, whatever. I don't know. Just the technological aspect. So, yeah, knowing about atom is an important fact. Second, how do I know about the atom? It's so small. I cannot handpick and tear out an atom. I can't. The only thing which is small enough to play with the atom is light. Fine. So let's study about light. How can we play with it? Now, studying about light, we had the notion of light being wave, light being matter. I guess de Broglie came up and solved the whole event. So, and also came up with a beautiful idea of matter wave. Now, Davis and German also pitched in, supporting the idea of de Broglie. So, de Broglie's idea was properly established. Again, jogging down the lane. Then after that, we came across the atomic models which we have around those times. Plum pudding, Rutherford, Bohr model. Bohr model being the successful out of the lot, and laid the foundation to quantum physics. Going down further down the lane, I had X-rays. X-rays, it became, let's say, a phenomena, or let's say a sign of style, so as to put it, because it was really cool, because it had a very small wavelength, high energy, very good penetration power, used for different medical uses and security purposes as well. And it was easy to produce, first of all, and cheap. That's the reason. Being human, you sort of look into these aspects. Then I became more destructive. I wanted to make, powerful, energy-giving substances, deal with those kind of stuff. So I dig into nucleus, how I can use the phenomenon of radioactivity to my purpose, how I can use those nuclear reaction to my purpose, setting up chain reaction. Right? So these are the things which we learned about the whole of atom, starting from outside, then digging in inside, electrons to nucleus. So that's how we played on. So in short, I have given you the total, let's say, a beautiful story connecting the different dots and different characters in the story. So if you have any more doubts, any let's say doubts or queries regarding this video, or let's say in general the doubts occurring because you have gone through the lectures, let's say the video lectures, and also referring to the books and made out some problems. So for more doubts and questions like these, you can log on to askIITians.com and ask for an expert and put out your questions like this. And also you can check out the new videos for different chapters of physics, chemistry, biology and mathematics in the same site of askIITians.com. So thanks to all of you. Bye-bye. Take care.